Okay, 4.1, data number 1, notes, definition of the absolute max and min. Let f be defined on the set D containing C. If f of c is greater than f of x for every other x, then it has an absolute max value of f of c on this domain of D at C. If f of c is less than or equal to every x for every x in that domain, then it has an absolute min. Basically, is it the biggest large, or is it the biggest value or the smallest value on its domain? Absolute extreme value refers to either absolute max or absolute min. So the definition of local max and local min is, suppose that C is an interior point of an interval called I, on which f is defined. If f of c is the largest x value for all x in that interval, then f of c is the local max. If f of c is the least value on that interval I, then it is a local minimum value of f. So the two conditions placed on this: f must be continuous, and f has to be on a closed interval. On a closed interval. Both of those are required in order for this coming theorem called the extreme value theorem to work. Okay, so the extreme value theorem, required knowledge for the exam, definitely. It's also called the Max Min Existence Theorem. A function that is continuous on a closed interval has an absolute max and an absolute min on that interval, for sure. But it has to be closed. So see, I have closed circle here and here. That can be denoted by, on the interval a to b, and the function must be continuous. So the theorem applies if those two are present. Local extreme point theorem: if f has a local max or min value at c, then f prime of c exists and f prime of c equals 0. Basically, here at our max value or here at our min value, the derivative will equal 0. But that doesn't mean that every time the derivative equals 0 that it's a max or a min, right? We have to have a change in concavity, right? So here we would have concave down. So the derivative will equal 0 at a max or a min. Okay, so the definition of a critical point is an interior point on the domain at which the derivative is 0 or the derivative fails to exist. Those are all called critical points. So steps for locating absolute extreme values on a closed interval, assuming f is continuous and it's a closed interval. We're going to locate those critical points. These points are candidates for absolute max and min. Then we're going to evaluate f at those critical points and at the endpoints, because the endpoints could be maxes or mins as well. We're going to choose the largest and the small values from step 2, and these values are the absolute max or min, depending on the outcome, whether they're the largest number or the smallest number. Okay, so first off, here's an example. We have to determine if we have continuity and a closed interval. Well, clearly there's a closed interval, and all polynomials are continuous. Okay, so we can check off those first two things. Is it continuous and is it on a closed interval? So the next thing we'll do is we'll find those critical points. Okay, finding the critical points, we're going to want to find the derivative of the function. So f prime of x. Polynomials are great. That'll be 4x cubed minus 6x squared. Okay, what we want is we want to know when the derivative is equal to 0. So what I would do is factor out a 2x squared. That leaves me with 2x minus 3. So my two critical points are going to happen when x equals 0 from here and when x equals 3/2. These are my critical values. Critical values. Okay, so what I want to do next in step 2 is I want to use my candidates. So use candidates to determine my max and min on that interval. So what I would use is my endpoints. So my endpoints are -2 and positive 2. My critical values are 0 and 3/2. And I'm going to look at the outputs for each of those. So I'm going to look at f of negative 2. I'm going to look at f of positive 2. I'm going to look at f of 0 and f of 3/2. I'm going to go off camera real quick and come up with those values. Okay, so I evaluated each of these by plugging them into f of x up here. And it looks like I get a maximum value here. And I get a minimum value here. So let's finish it off here. So we could say that the maximum, absolute max on this interval would be at the point negative 2, 32. And the absolute min on this interval would be at the point 3/2, negative 27/16. All right, let's look at the following here. Again, I want to show that it's continuous on this interval, as well as it's on a closed interval. So first off, we've kind of taken care of the continuity piece, because if x is greater than 0, then we don't have an issue in the denominator, and the natural log of x also is continuous on that domain from 0 to infinity. We have a closed interval here, so we're good to go. So I'm just going to go ahead and calculate the derivative. So f prime of x is low d high minus high d low all over low squared. Okay, I'll simplify that. Looks like we get 1 minus the natural log of x over x squared. Alright, so step number 1, let's find our critical values, our critical points. Let's find those by setting the derivative equal to 0. I'm going to multiply both sides by x squared. Looks like I get still 0 is equal to 1 minus the natural log of x. And so if the natural log of x equals 1, then x has to equal e. Okay, and what you'll notice here is I only have one critical value, and it's also one of the endpoints. So my my candidates in step 2, my candidates will identify my max and min, and I only have two values, right? At x equals, I'm going to check the endpoints as well as where the derivative equals 0. This one acts as both the at right endpoint and one of those critical points as well. So I'm going to go ahead and off camera find f of 1 over e and find f of e. And it looks like the question is just asking for the max value, so I'm just looking for which of those two is larger. Okay, so when I evaluated these, I got negative e and 1 over e. 1 over e is larger since it's positive, even though it's not a large number. So that would be the maximum value for that function on that interval. All right, a particle moves along the x-axis with position at time t given by x sub t between 0 and 2 pi. Part A, find the time t at which the particle is farthest to the left and justify your answer. I'll put a little work down and be back. Okay, so first off, what I'd recognize from the wording is that farthest to the left with particle motion would mean an absolute minimum. So I take my position function, I take its derivative, which using the product rule gives me the following. And we want to know when this thing equals 0, right? This right here will never equal 0, but this will equal 0, right? Basically, if I say I want to know where negative sine t plus cosine t equals 0 is true, that means I want to know where the sine of t is equal to the cosine of t, which happens at two places, right? So these are my critical values at t equals pi over 4, where both of them are positive 1 over root 2, and where t equals 5 pi over 4. All right, so if you look at your unit circle, sine and cosine are equal there and there. You might be tricked into thinking in the second and the fourth quadrant, but the cosine is negative while the sine is positive, so they're not equal. Okay, so we've got these critical values here, and then we also want to test those endpoints at 0 and 2 pi. So my values are 0, pi over 4, 5 pi over 4, and 2 pi. So I want to take position of each of those and find out which one is minimum. I'll come back with an answer momentarily. Okay, so I didn't entirely calculate them because I didn't have to. You'll see at the endpoints we get position as 0, and on the values in between, I'll get a positive value here for the position when t equals pi over 4, and I'll get a negative value here. So I know this will be my absolute min. So I know when t equals 5 pi over 4, I get a minimum. So x of 5 pi over 4 is going to be equal to e to the negative 5 pi over 4 times the sine of 5 pi over 4. And if I don't have a calculator available, that's exactly how I'd leave it. Otherwise, you can go ahead and work your way through that and then give an approximate answer. Okay, example 4, this is a calculator allowed problem. Let f be the function defined by the following. For x between 0 and 3, which is a closed interval, find the absolute max and absolute min value of f. Justify your answer. Okay, so in order for the natural log of x plus 1 to even exist, x has to be greater than negative 1. Because the natural log of 0, which would be where x equals negative 1, does not exist, right? So we have to translate that domain, and conveniently, negative 1 is not even on the domain, so we're good to go. Okay, so I'm going to go off camera for a moment. I'm going to find the derivative. You could too as well. Come back in a moment, I'll have that. Okay, so using the derivative of the natural log as well as looks like the chain rule in the second piece, I come out to get this as my derivative. This derivative also would not exist at negative 1, right? If x can't equal negative 1, and therefore I'd have to check like a second layer of that. But again, that's not on this interval, so we're good to go. So all that I want to know is where this thing equals 0. So 1 over x plus 1 minus 2 sine x cosine x equals 0. I'm going to need my calculator for this because I don't know off the top of my head, unless you do, where these two are equal. But I'm going to go ahead and calculate those values and check endpoints as well in just a moment. So I'm going to graph that. Alright, so I found graphical critical values of 0.398 and 1.351. We got endpoints here of 0 and 3. When I plugged each of those in to the original function, I got a min value. I get a min value here at 1.351, and I got a max value at x equals 3. Justifying my answer, basically, I can just say that checking each of those points, the endpoints and those critical values, those were the minimum value and maximum value as outputs. Okay, so for number 89 here, 2008 multiple choice, if I know f of negative 2 and f of 2 both equals 0 on this continuous closed interval, if there is no c where c is between those two values for x, where the derivative equals 0, so there's no value where the derivative equals 0, right? I mean, someone's going to think, well, straight line, right? Well, the derivative is 0 everywhere on that. So that means that the derivative is going to be positive for a certain point and negative for a certain amount of that interval, but at some point it kind of skips 0, right? So that's a point of discontinuity. So that means there's some value k in that interval for which there's a cusp or there's a sharp turn where it is not differentiable at that point. So therefore the answer here must be E. That is 4.1, day number 1, on whatever the heck we just did. What did we do? Local mins, local max, extreme value theorem, and all of that good stuff. So we'll see you on the next lesson. Have a great day.